Welcome. Now, what we are going to do is we have looked at fluid statics, we have looked at macroscopic balances, which involves pressure forces, momentum forces, gravity force, and buoyancy force, and so on. And now we are going to come to a more important part of our course related to energy. So, we are going to start talking about energy. Remember, in the first lecture, I told you about taking water from, let's say, ground floor to the top floor, and how much energy would be required. So that's the question that we are going to ask. What is the geometry that is there, how much energy is required, and how much flow we are going to get. So just to get you started, what we will look at first is just a quick revision of what we have done. So we have done these two parts. We have done fluid statics, we have done macroscopic balances, and now we are going to start looking at energy. Another name for that energy equation is Bernoulli equation, and we are going to look at engineering applications, and more particularly we are going to look at pressure drop in pipes and fittings and piping systems, and how to measure flow rates as well. So it's a slightly longer part of the course and a very important part of the course. Just to quickly recap what you have done in the first two modules. First of all, can you write what is meant by kinetic energy correction factor? Can you write what is meant by momentum correction factor? What is the value of this kinetic energy correction factor, momentum correction factor for laminar flow as well as turbulent flow? Write an expression for rate of flow of angular momentum, and what is the meaning of that angular momentum, and what is the meaning of the word torque. It is like when we are talking about systems which are rotating, let's say shaft is rotating, the turning action, the force of the turning action is measured, is called as torque. So think about what these mean and how that torque is related to power that is either generated or power that needs to be supplied to keep a certain rate of rotation. So revise these concepts and then go forward. So what we are going to talk about is we are going to talk about any equipment, right? This could be a pipe, this could be a compressor, this could be a pump, this could be some reactor, this could be some distillation column, whatever that equipment be. Some flow is going to come into that equipment, some flow is going to go out of that equipment. We might supply some energy to that equipment, and some of the energy would be dissipated as heat, as in overcoming friction within that equipment. Now we talked about laminar flow, where layers are sliding over one another, and when these layers are sliding over one another, they will experience a friction. So wherever flow is taking place, there is a certain amount of friction that is happening, and so energy is required to overcome that friction, and finally that energy is dissipated as heat. Now, when we talked about forces and when we talked about energy, we talked about different kinds of energy. First of all, we talked about kinetic energy, and when we write half rho v square, we wrote that we thought about this quantity as energy associated with the velocity, with the kinetic energy associated with the fluid per unit volume. So half rho v square is nothing but kinetic energy associated with the fluid per unit volume. Similarly, potential energy, when we say that a certain substance is at a certain height or a certain fluid is at a certain height, there is a certain amount of potential energy. And recall from our lectures that this potential energy we have been talking with respect to some reference level. So if I say reference is ground level, it is at a height of 1 meter. So the potential energy is corresponding to that 1 meter of height. And so if I multiply by the h by rho g, that will give us the potential energy. So again, h rho g is in terms of joules per meter cube. So if you had a mass of 1 kg in your 11th standard and so on, when you were talking about uh, uh, let's say a mass of 1 kg is at a height of, let's say, 1 meter, you said mass multiplied by g multiplied by h, that's the potential energy, because that's per unit kg or per unit mass of that substance. So h into g tells us per unit mass of that substance. But if I multiply by rho, that will tell us the that will tell us how much energy is associated per unit volume of that fluid. So H rho g tells us the potential energy associated per unit volume of that fluid. Now when we said pressure multiplied by cross sectional area, that's a force. So pressure is nothing but force per unit area. Now if I displace that force by a certain distance, let's say 1 meter, then that will give me the energy change for making that pressure force go by 1 meter, or the energy that is acted on to make that object go by 1 meter. So in a sense we can think about pressure as Newton per meter square, but we can also think about it as joules per meter cube. That means so many joules would be required to make that pressure force go through a distance of 1 meter. So energy associated with pressure of the fluid, we can think in terms of P, which is nothing but joules per meter cube, energy per unit volume of the fluid. In addition to this, you would talk about internal energy. Sometimes it will be called as E, sometimes it will be called as U. So in thermodynamics course next semester, you are going to call this as U, and enthalpy you are going to call as H, but it doesn't really matter right now. These two energies are important for whenever we are talking about gases and whenever we are talking about large temperature changes. And these right now, for the purpose of this course, we are not going to consider these two. So these two will come in your second year. It will come in two courses, thermodynamics course, as well as there is a course on generation and transmission of mechanical power. There we will talk about gases under high pressure, turbines, and so on and so forth. So there these kinds of considerations become important. Right now, for the purpose of this course, we are not going to worry about these enthalpy and internal energy, and we are only going to work with these three kinds of energy: kinetic energy, potential energy, and pressure energy. And we are in a sense you can think about this as these three as some form of mechanical energy, and therefore this macroscopic energy balance we are going to call in terms of mechanical energy balance. Okay. So right now what we want to do is we want to write energy coming in because of these three forms, energy going out because of these three forms, right? So these energies, they are going to be associated with the flow that is coming in. So we would like to write these three quantities for the flow that is coming in and the flow that is going out. So these three quantities we will write with respect to the flow coming in and going out. We may also have some energy coming in. We may supply electrical energy, we may supply some mechanical energy, and energy dissipated as heat. So if we write a balance for this is what we should be writing. So the rate at which energy comes in because of the flow, okay, it will be half rho v square v1 square at location 1. Let's say entry we call as location 1, exit we call as location 2. Let's just write that as well. Entry we want to write as location 1, so this is our location 1, and exit we would like to write as location 2. It is exit of flow. It is where flow is going out, mass or a fluid is going out. Okay. So this is kinetic energy per unit volume multiplied by volumetric flow rate, potential energy per unit volume multiplied by volumetric flow rate, pressure energy multiplied by volumetric flow rate. This will give us joules per meter cube multiplied by meter cube per second. So that will give us joules per second, or nothing but watts. So this is the rate at which energy comes in terms of watts. Similarly, I might supply energy at a certain rate to the equipment. Either it could be mechanical or it could be electrical. So let's say W is what I supply. The rate at which energy goes out at location 2, again we can write from half rho v2 square into q, h rho g into q, v2 into q. Again this will have units of watts. Now energy is required to overcome friction within this equipment. We will slowly see what that friction is and how to calculate that. But right now some energy is lost to overcome friction. So that, let's say, we write by WF. And so in minus out, if we do in, out, lost would be equal to the energy rate at which energy is accumulated within the system. And if we are talking about steady state, then the rate of accumulation would be 0. So our equation would be now half rho v1 square multiplied by q. H1 rho g q P1 q plus energy that I supply must be equal to half rho V2 square into q, H2 rho g into q, P2 into q plus whatever energy is lost in overcoming friction. Now that's our mechanical energy balance, and we are going to use this equation again and again and again throughout, not just this course, throughout our life for your successful professional career. This is one equation that you will need to use again and again and again, and therefore this equation is very useful for us. We will see different forms of this equation. Question that I am posing right now: do you think this equation is correct, or any correction is required in this equation? Think about this, pause the video. Okay, so here is the answer. Now we have talked about energy per unit volume, kinetic energy per unit volume of the fluid as half rho v square. But that's assuming velocity is uniform. What if the velocity profile here is not uniform, but let's say parabolic? What if the velocity profile here is not uniform, but some other shape? So that means what we have calculated based on average velocity, if we calculate this term based on average velocity, then I need to multiply this by a kinetic energy correction factor. Similarly, here I need to multiply by a kinetic energy correction factor. And recall from our last video, the kinetic energy correction factor, momentum correction factor, alpha and beta. Those are the correction factors that we require now. That's why we did them beforehand. That's why we did them in the previous lecture. So if you're not clear about that, go back, revise that, and then we will talk about it. Okay, so what we need is the correction factor. So correction factor now is going to be in terms of alpha. So alpha at location 1 and alpha at location 2. So these two correction factors we require, and therefore this is the equation that we should be utilizing, not the earlier equation. Okay, let's go forward. Let's think about this in some different ways. So this equation tells us the rate of energy or power in terms of watts. But if I multiply, so if I divide throughout by Q, okay, and if I divide throughout by rho, which means I am dividing by mass flow rate, I will get an equation not in terms of, I will get an equation in terms of watts. So this equation would now be in terms of watts, and I have divided by mass flow rate. Mass flow rate is kg per second, right? This is nothing but watts into second joules per kg. So now this equation is in terms of energy per unit mass of the fluid, So just to put it into perspective, look at this term H1 into G. That's mass per unit. That's the potential energy per unit mass, right? So this is right. So this is joules per kg per unit mass of the fluid associated at location 1 and at location 2. So at these two locations, what is the energy associated with the fluid in terms of kinetic energy, pressure energy, potential energy, and location 2, what is the energy associated with the fluid in terms of kinetic energy, pressure energy, and potential energy. Now, rather than talking about, say, potential energy, what we do talk about, potential energy, we talk in terms of height. So it is very easy to understand that if potential energy, if the object is at 5 meters, potential energy corresponds to 5 meters, rather than saying that it is 5 into 9.81, almost like 50 joules per kg. That's very weird to think about. So rather than talking about H into G, I could even divide this equation by G throughout, and then we will get alpha 1 v1 square by 2g. I have divided by g, h1. So now this is much easy to understand, p1 by rho g, and same way w by rho gq I can write, and alpha 2 divided by rho g, H2, P2 by rho g, W by rho GQ. Now this H1 is like height. So similarly, this quantity we call as kinetic head. This also is height. It is height associated with the kinetic energy. So we call this as kinetic head. Right? This quantity we can call as pressure head. It has units of meters. It is equivalent to a height, but we don't say pressure height. It is an energy, so we say head, we say pressure head. Similarly, this W by rho QG we can think in terms of head added by whatever external work we have done, whatever extra power that we have put in, whatever extra mechanical energy we have put in. And similarly, this WF by rho GQ we can think in terms of head that is lost in overcoming friction. So this form is what we use all the time. Let's illustrate this with the problem that we were thinking about. We were talking about some liquid to be taken from, let's say, ground floor to the top floor. Let's think about that. So imagine that there is water in some tank on the ground, and we want to take this water from this location to an overhead tank. That's what we were talking about in the first part of the course. Okay, so what is the energy available with this fluid in terms of head? It is kinetic energy, alpha 1 v1 square by 2g, potential energy, pressure energy. That's the energy that is available. Alpha 2 v2 square by 2 h2 p2 by rho g. That's the energy that is available at location 2. Which is larger? So if I say h1 is 0, ground floor, h2 is, let's say, 10 meters, 20 meters, 30 meters, right? So this h2 is larger than h1. Suppose both these tanks are open to atmosphere, then this p1 and p2 will be the same. They will just cancel out. Let's say tanks are of the same size, then v1 square by 2, v2 square by 2 will cancel out. That means the energy associated with the fluid at location 2 is more than energy associated with location 1. So this fluid will try to in fact go from 2 to 1. But that's not what we want. What we want is to take fluid from location 1 to location 2. So the way we can do that is only if we add energy, and we are going to add energy by the help of a pump. So I will need to add energy to make it go from 1 to 2. Okay, and in the fluid in going from 1 to 2 through this pipeline, it will have to overcome friction, and therefore head or friction energy is lost in overcoming friction in the pipe. So that's the meaning of that Bernoulli's equation, and then we are going to use this Bernoulli equation now to calculate. So the question is, how much pump power is required to make this water go from location 1 to location 2? Just to get you started, let's just rub out all this. Right. So what we are saying is V1 and V2 are small because tanks are big. The levels in the tank change very slowly. So V1 and V2 are small, and they are also nearly equal. So I can even cancel these two terms. Right. These two terms can be cancelled out. This whole term can be cancelled out. So the pump power, the head that needs to be added by the pump, is equal to the potential energy, potential head height difference, pressure height difference, pressure head difference, and in what is required to overcome friction. So this is easy to understand. H2 minus H1 is easy to understand. I know the level of tank 1, I know the level of tank 2. Just subtract them, that's H2 minus H1. P2 I can measure, P1 I can measure. We have seen how to measure pressure in tank 1, how to measure pressure in tank 2 in our lectures on fluid statics. So before we can calculate the head required by the pump, we need to know how to calculate this friction HF. Okay, and the pump power required now. So if I use this equation, if I know how to calculate HF, then I can calculate HP. And once I calculate HP, once we calculate HP, what is the power required? Go back. Where has HP come from? It has come from here. W by rho GQ is HP. So W, power added by the pump, power required by the pump, is HP multiplied by rho GQ. And I can even think of it as HP into rho G multiplied by volumetric flow rate. The head added or energy added per unit volume multiplied by volumetric flow rate. So first and foremost, I need to know, how do I estimate this HF? How do I calculate this HF? How do I calculate the friction that is required or the friction that needs to be overcome in this pipe? And that's a very, very important part, and very important to estimate this value accurately. So let's just try to see how to estimate this friction. Okay, so we are going to estimate this friction now. So think about a pipe. So let's say there is a pipe here. Let's say there is a pipe here. Let's say pipe is horizontal just now. So in order to make the fluid flow from location 1 to location 2, I need pressure at location 1 that needs to be higher than that at location 2. And fluid is going in this pipe, right? So if I write Bernoulli equation from here, so alpha 1 v1 square by 2g, if I write Bernoulli equation for this change, this fluid going from 1 to 2, v1 and v2 are the same. We saw material balance, cross sectional area of the pipe is same, so v1 and v2 gets cancelled out. h1 and h2, pipe is horizontal, so that gets cancelled out. HP, there is no pump between 1 and 2, so this is 0. So HF would be nothing but P1 minus P2 by rho g, or delta P by rho g. And that's why in the manometer, first part of fluid statics, we saw how to measure this pressure difference. So the pressure difference that we measure is directly related to the frictional head lost. It is a representative of how much friction is occurring. Now let's see a little bit about this friction. Let's see about this friction. You have seen that in laminar flow, these layers are sliding one over the other. You recall? So when this layer is sliding over one another, there is friction between layers. Also, these layers are sliding next to the walls. So there is a friction between the wall and the fluid. And even when we saw turbulent flow, you can think of turbulent flow. Turbulent pipe flow, yeah. When we saw turbulent flow, you can see that there are packets of fluid going from one place to another place. So these packets of fluid are going from one place to another place. So if I say that there is one layer sliding over another layer, that's friction. Or if this is wall of the pipe and fluid is flowing, there is friction there. Okay. Now in turbulent flow, these layers are not uniform, they are in terms of packets of fluid. So whenever there is a packet that is going along, or two packets, one packet sliding over the other, there is friction there. Right? So what we will do is try to estimate this friction. Try to estimate this friction now. Okay, so if I write a force balance on this pipe, P1 minus P2 into cross-sectional area here, and P2 multiplied by this cross-sectional area, that is the net pressure force that is acting on this fluid. Now that is balanced. If the flow is at steady state, this will accelerate the fluid, but at steady state fluid is not accelerating. So this force must be balanced by frictional force at the wall of the pipe, and that frictional force we are going to write in terms of, it is going to be dependent on the surface area of the pipe, and we write in terms of frictional force per unit surface area of the pipe. So this is, let's just rub this, let's write this properly. This is the surface area, and this quantity tau W is the frictional force per unit surface area. We are going to call this as wall frictional force or wall stress. Is force per unit area, therefore we call it as stress, but it is force per area, not perpendicular, but it is the surface area along the flow, therefore we call it as stress, not pressure. It is force per unit area, but it is not pressure, we call it as stress, and we call this as wall stress. Now, so if I have to get friction factor, now if I have to get this HF, what I will do, H is delta P by rho g. If I divide this by delta P by rho g, this tau W will be, if I divide this by rho g, so HF, capital HF would be delta P by rho g, you see, and this tau W can come from here. So now if I have to estimate friction, now I will have to give you data for this tau W for all kinds of pipes in all kinds of fluids, right? And then it will become very cumbersome. So the way we try to do is define something called as friction factor. So we define this friction factor as tau W divided by the kinetic head that is going in the pipeline, half rho v square, and this v is nothing but we average velocity in the pipe, and because we have used the kinetic energy correction factor, so even if the flow profile may not be uniform, but we are going to use the average velocity for calculating this kinetic head, and we are going to use the average velocity for calculating this friction factor. So then this becomes a good way of making things dimensionless, where tau W has units of Newton per meter square, and kinetic head half rho v square also has units of joules per meter cube or Newton per meter square, and therefore this becomes a dimensionless number. Now I don't have to worry about whether flow is 1, 2, 3, 4, 5 meters per second. If I tell you how this dimensionless friction factor, what is the value of this dimensionless friction factor, then you can use this to calculate the tau W and therefore the energy required HF to, for any fluid. I just have to give you density of the fluid, I just have to give you velocity of the fluid, right? So if you rearrange from this expression, let's rub these arrows now. If we write from this expression, right, if we write from this expression now, this expression I can rearrange as tau W would be delta P d by 4L. So now friction factor I can define as tau W divided by half rho V average square, which if I substitute this equation, I'll get delta P d 2 rho V square L. And then delta P, that is the pressure difference required across the two ends of the pipe, will now be 2 multiplied by this friction factor rho V square L by D. And HF, if you want to write, it is delta P divided by rho G, so HF would just become 2F V square L by dG. So HF would be, you can get from this equation, 2F V square L by dG divided by dG. Okay. So that's the advantage of using this friction factor in a dimensionless form. I can use this equation for any density of the fluid, any velocity of the fluid, any length of the pipe, any diameter of the pipe. Otherwise, I will have to give you friction for all kinds of fluids, for all kinds of pipe lengths, for all kinds of diameters, and so on and so forth. So this friction factor defined in this manner is called as fanning friction factor. Some other people define friction factor slightly differently. They defined it using this expression. Fd, another kind of friction factor, would be delta P divided by half rho V square multiplied by d by L. Multiplied by d by L. And then you can rearrange from here. This will give you that tau W is delta P d by L. Okay. This friction factor is called as Darcy friction factor. Now, civil engineers, mechanical engineers use this Darcy friction factor very often, whereas fanning friction factor, chemical engineers use this very often. The difference is just the way it is made dimensionless. Fanning friction factor uses tau W and half rho V average square, whereas Darcy friction factor uses delta P divided by half rho V square into d by L. Well, obviously they are related to one another. Darcy friction factor would be related to 4 times the fanning friction factor. You just have to use these two definitions, this definition and this definition. Okay. Finally, whether I use Darcy friction factor, whether I use fanning friction factor, I am going to get the same value of HF, because the HF related to Darcy friction factor or HF related to fanning friction factor, that relationship is slightly different. It's different by a factor of 4. Okay. Let's just see a little bit more into this. Okay. Let's just see a little bit more into this. Turns out that people measured this Darcy friction factor or fanning friction factor. How would I measure? I would measure the pressure difference required for making a fluid flow, P1 minus P2, and you're going to do an experiment. You will measure this P1 minus P2 for a certain amount of flow. We are going to measure the flow. So in short, we are going to measure this P1 minus P2. You're going to calculate HF. You're going to calculate tau W, and you're going to calculate friction factor, because you are going to measure the flow. So this is what people did. They measured the friction factor for a variety of different pipes, for a variety of different fluids, and they came out with this expression or this relationship. The fanning friction factor or Darcy friction factor, it is Fd here. So this is Fd, Darcy friction factor. They related this to Reynolds number, Re. And you see two different regimes. One regime where Reynolds number is less than 2100. That's called as laminar regime, laminar flow, layers sliding over. And there you find that friction factor is inversely related to Reynolds number. Whereas in turbulent flow beyond 2100, between 2100 to about 4000, 3500, 4000, that's called as transition regime. So this regime is our transition regime between 2000 to 4000. Beyond 4000, what people found is that friction factor reduces, but not linearly. It is a gradual reduction. And it depends on something about called as roughness, how rough the pipe is, whether it is the same material of construction of the pipe, same fluid, but if pipe is very smooth or pipe is rough, the friction factor changes based on that. And then that is called as a relative roughness. We'll see what that relative roughness means. And now at very high Reynolds number, we will see that friction factor is practically independent of Reynolds number. Friction factor is just a horizontal line, but it depends on the roughness of the pipe. The more rough the pipe, the higher the friction factor. Similarly, fanning friction factor can be related to Reynolds number. This, rather than calling it as NRE, this is just our Reynolds number. So again, in the laminar regime, this is 1000, this is 100, 200, 300, 400, 500, 600, 700, and so on, 1000, 2000, 3000, 4000, 5000, 10,000. So this is log scale, and this also friction is the log scale. Is in a log scale. This graph paper is called as log graph paper. You can use it in Excel very easily. So below 2100, flow is laminar, and beyond 4000, the flow is turbulent. Okay? And you see that in the laminar regime, friction factor is 16 by Re. In the turbulent regime, again it depends on the roughness, and here is typical roughness of the pipe. Now here it is written in terms of K by D. It's the same as epsilon by D in the previous case. Okay? Here that value of K is written for different types of pipes. It's a concrete pipe, cast iron pipe, galvanized iron pipe, steel pipe. Now, so if I want to estimate friction head loss due to friction, energy lost in order to overcome friction, I will have to use it from here. I will have to calculate from here, and the F I will get from here, either Darcy friction factor or fanning friction factor. So that means wherever I'm going, if I need to calculate friction factor, I'll need to carry this chart with me. Good idea? Bad idea? Not a very good idea to carry this chart with you all the time. So what people did, they have developed expressions, mathematical relationships between F and Re or FD and Re. Okay, just to tell you this roughness, so if you look at a pipe surface in a microscope, you will see that pipe surface is not uniform, it is wavy, it is rough. And then this height of that rough part is called as epsilon, and is expressed in terms of epsilon by D. So epsilon, values of epsilon in terms of millimeters or in terms of feet are given for different pipes, and this changes with respect to operation. So you say you can take a steel pipe, brand new, it will have a epsilon of 0.05, but if it is rusted, epsilon can be 2. You see how much extra friction will go, how much extra friction will be caused. Oops. How much extra friction will be caused. 0.05 becomes 2. It has become 40 times. Friction factor will increase by a factor of 40 almost. Right. So this is how this is the importance of this roughness parameter, and there are people have given equations. So Holbrook gave an equation 1 by root FD minus 2. This expression, this requires iterative solution. So if I know Reynolds number, let's say 10,000, if I know epsilon by D, I have to iteratively calculate this FD because it is there in both the places. It's a for Darcy friction factor. Swami and Jain 1976 gave another correlation for FD. Halland 1983 gave another correlation. So these equations are a sort of concise form of these charts. So I don't have to carry these charts with me for calculating the power required. I just have to use one of these equations. There's another equation, Churchill 1977 gave in terms of fanning friction factor in terms of two constants A and B. They are defined here. Okay. What we will do now is we will quickly estimate the values of friction factor by different methods. Okay. So let's just say Reynolds number is 10 raised to 5. Epsilon by D is 0.001. Let's calculate this friction factor by different methods and see how different they are. So if I have a smooth pipe here, smooth pipe, this is for a smooth pipe, the lowest value where epsilon by d or k by d is 0. So if I use that 0.079 re raised to minus 0.25, so 0.079 10 raised to 5 raised to minus 0.25, you will get friction factor, fanning friction factor to be 0.0044. If I use another expression for smooth pipe, 0.046 re raised to minus 0.2. So these two expressions are only for smooth pipes, not for rough pipes. If I use this expression, I will get friction factor 0.046 re raised to minus 0.2. It will be 0.0046. You see, very similar. If I use rough pipe now, Colebrook equation, this is the equation. Substitute, get it for yourself. Iteratively get a value of FD. You can use a calculator. You will get 22.19 into 10 raised to minus 3. And fanning friction factor will be Darcy friction factor divided by 4. You will get it as 5.55 into 10 raised to minus 3. So now compare. If it was a smooth pipe or a rough pipe, friction factor would be 20% more for an actual rough pipe rather than smooth pipe. So it's not correct to use the smooth pipe equation. We don't use this when we know that pipe is rough. If you just want to check with the chart, these charts are called as Moody charts. Person who drew them for the first time. Okay, let's say Reynolds number is 10 raised to 5, epsilon by d is 0.001. Let's look at the Darcy friction factor chart. 10 raised to 5, this is 10 raised to 4, this is 10 raised to 5. And epsilon by d is 0.001. That is here, this point. The friction factor, Darcy friction factor is something like this. 0.002 is here, 0.003 is here, so it's like 0.002, 0.021, 0.022, 0.023, so forth. So it's 0.022 from the chart, right? 0.022, and 1/4 of that would be the fanning friction factor. Use some other equation, let's say Swami and Jain equation. Again, you can solve for yourself, do it for yourself. I have already done that for you. You will get fanning friction factor 5.58 into 10 raised to minus, just 0.5% more than the Colebrook equation. If you use Halland equation, you will get 5.49 into 10 raised to minus 3, just 1% less than the Colebrook equation. Okay, so whether you use Colebrook equation or Halland equation or Swami and Jain equation or the Churchill equation, you will get almost the same values. Don't worry about too much about which equation you use. It is very different from the smooth pipe. Why? Because pipe is not smooth, pipe is rough. It has a roughness of 0.001. Okay. And therefore, we should not be using smooth pipe equations, we should be using rough pipe equations. And any one of these rough pipe equations will almost give you the same value. So that's the advantage of these charts. We can calculate the friction factor knowing Reynolds number and knowing knowing how rough the pipe is. We can calculate the friction factor very easily. And now we will try to use this into our calculations. Just to give you a flavor of where these things are important, these are just some pictures of typical plants in a process. You see, so many pipes are there. In fact, only thing that you can see is pipes. One pipe, two pipes, so many pipes. And piping is a very complicated subject, complex subject. But you can get it very easily once you start looking at it from Bernoulli equation. We will do some problems and it will make you more comfortable. So you see, piping is a very important part of a plant, and friction in pipe is very important. That's why we are going to devote so much time to this. And you see, there are pumps aligned here. You see, all these green things are pumps, and how nicely they are arranged in a line, and then controls and all those things are there. They feed different substances to different pipes and so on, different locations, reactors, columns, and so on and so forth. So this is how a 3D layout of a plant looks like. So piping is very important, and therefore we are going to spend a lot of time on piping. Just to give you one more one more thought, and then we'll stop here for this lecture. These pipe sizes come in standard sizes, so they are referred to by something called as a nominal size. The nominal size is like a roll number, right? So there is a pipe of 1/8 inch, 1/4 inch, quarter inch, 3/8 inch, half inch, 3¼ inch, 1 inch, and so on, 2 inch, 3 inch, 4 inch, and so on. So this is like, it does not mean that the pipe diameter is this. It's just a way of representing, right? Pipe diameter is approximately this. So for example, if we take a 1 inch pipe, you would expect diameter, 1 inch is 25 millimeters, you would expect diameter to be 25 millimeter. It's not exactly 25 millimeter. It depends on the thickness of the pipe. You see, if it's a 1 inch pipe, outside diameter is not 1 inch, it is much larger than that. Thickness is written in terms of something called as a schedule. So you have two schedules, schedule 40 and schedule 80. So if it's a 1 inch pipe, schedule 40, the inside diameter where flow is occurring would be 1.049 inches. It will be 26.6 millimeters, approximately 1 inch, but not exactly. If it's a schedule 80 pipe, the inside diameter would be 24.3 millimeters. If it's a 2 inch pipe, 2 inch schedule 40 pipe, inside diameter would be 2.067 inches or 52.5 millimeters. If it's a schedule 80 pipe, it would be, inside diameter would be 49.2 millimeters. So this inside diameter is what is available for the flow of fluid, and once we start using in our calculations, you will see for yourselves. So we'll stop this lecture here. We'll start using all these concepts in subsequent lectures in making all these calculations. And what calculation we are going to do? We are going to do calculation for energy required, power required for making water flow from one tank to the other tank, from ground floor tank to the top floor tank. How much power, pump power is required, and that's where we are going. We are going to use all these concepts to get to that calculation. Okay. We'll see that in the next lecture.